2021 meeting will be presented via Zoom by Dr. James Lamsdell of West Virginia University. He studies Paleozoic arthropods such as eurypterids and xiphocerans, that's horseshoe crabs and their relatives. And he's going to talk about the Ordovician Big Hill Lagerstätte in Upper Michigan. In April, our speaker will be Dr. David Landon from the University of Massachusetts, Boston. Dr. Landon is one of the project directors for the Plymouth Colony Archaeological Survey, and they have been working to uncover the remains of the original 17th century settlement. And tonight, our speaker is Dr. Gaia Stucky de Quay. Gaia is a member of the Planetary Geosciences Group at the University, or was a member of the Planetary Geosciences Group at the University of Chicago, and the Center for Planetary Sciences at University College in London, where she received her master's degree. At Imperial College London, she was a member of the Earth and Planets Group and earned her PhD. She is currently part of the Planetary Surface Processes Group at the Jackson School of Geosciences at the University of Texas at Austin. And her program tonight is called Assessing the Early Mars Hydroclimate Using Paleolake Geometries.
Perfect. Thank you for the introduction. Am I free to start?
Yes.
Awesome. Okay. I realize now I've slightly tweaked the title, but it should be the same thing. I'll just share my screen.
By the way, if you're not muted, folks, please do, unless you're going to have a question.
Just making sure. So can you guys see the full presentation on this screen?
Mm-hmm. Yes.
Perfect. All right, then without further ado, I will start. Thank you, first of all, for inviting me. I'm very happy to be here and talk about Mars, my favorite thing. And as you guys probably know already a little bit, Mars is a very different planet to Earth. It's very cold, very dead landscape, and there's not much going on now. You've got a very thin atmosphere. And in terms of surface processes, so things changing on the surface, it's just not quite comparable to Earth in the way that we have so many different forces like tectonics and erosion happening at such large scales. But we do know, however, that Mars many, many billions of years ago was quite dynamic, just as dynamic as Earth. And in many ways, it was very similar to early Earth billions of years ago. And it did have abundant water, even though it has none now, and it had a really vigorous hydrological cycle. And we can tell all these things just by looking at pictures of Mars. So the one you can see here in the background, for example, shows that there was a lot of surface modification in the form of rivers and lakes forming on Mars. And so we'll dig a little bit more into that and the surface of Mars in the next few slides. But first, I wanted to talk a little bit about how you probably see headlines about Mars. Every year there's a new article talking about how we found water on Mars. And so it's a little bit confusing to understand and digest how water actually works on Mars. What do we know about water on Mars? Because there are so many different levels to it. We know that water does exist on Mars, but most of it right now, all of it is frozen, and a lot of it is in the subsurface or in the poles. And so when we talk about Mars on Earth, what we really want to know is, was there liquid water on Mars? How much liquid water was there on Mars? Was it on the surface? And all of these questions are hugely important for understanding habitability. And so we want to know, could we have hosted life on Mars billions of years ago? And how would that have worked? Would that have been a similar situation to Earth? And could we have preserved that? So when I talk about water on Mars, we still don't really understand the role and how it shaped the surface. And this is extremely difficult to constrain because it was so long ago, right? And so to delve a bit deeper into that, maybe just going to go back a few years as well. This is, some news that came out quite a few years ago, so in the beginning of the 1900s, which Percival Lowell was actually one of the first people to, properly point a telescope at Mars. And what he found, or what he thought he found, was a wide array of channels that were actually canals that joined different cities and civilizations on Mars. So all of these straight lines built by these aliens on Mars that connected this huge developed civilization. And so he wrote extensively about this, and it was quite the shock for everyone. But we know now that this is actually not the case, sadly. And but it's not completely untrue. So the reason he thought this is obviously because there are some incredible large planetary scale channels that do like basically cross-cut the entire planet. And so we actually found this more recently. So this was more in the 1970s when we sent our first orbiters to Mars. So for example, the Viking orbiter was able to look and image for the first time some of these enormous channels that are kilometers in scale, such as this one. And so when we know now that their topography looks something like what we would see on Earth, of course, without the water. So these big canyons with these steep walls that used to host these massive rivers. And so this is kind of what we're looking at when we're trying to understand the surface processes on Mars and trying to look at these channels to figure out, okay, well, how much water do you need to be able to build these? And so since then, we've actually had vast amounts of evidence. So we have several orbiters, we have landers on Mars. And so generally, the evidence for water comes in different shapes and forms. So firstly, you've got these eroded valleys that you can see here. So these are actually what we call valley networks on Mars. So these are channels that were eroded in, and they are very dendritic. So they have loads of tributaries, and they look very similar to rivers that would be fed by rainwater or snowmelt on Earth. But you also have the other side of the coin, which is the depositional side. So where the eroded sediment then gets deposited. And so you've got these huge deltas and fans that suggest that there was a huge standing body of water where these were deposited for a long amount of time. And that's just what we see through remote sensing, through orbiters, right? So if we look closer and we have our rovers that are on the surface, we see equally compelling evidence for significant water activity. So we have these pebbles that suggest a river environment that they were rolled in. We've got these layered sediments and crossbeds. But so for this talk, we're mostly going to focus on this remote sensing aspect because I'm more focused on the large scale patterns of river and water shaping the surface of the Earth. So we'll focus on these remote sensing observations. And so I wanted to talk to you a bit more about the climate of Mars, or the paleoclimate, because this is what we're really trying to understand. So a lot of geomorphologists, or people who understand landforms and landscape evolution, think or suggest that a lot of these must mean that there was a lot of precipitation on Mars for many, many, maybe even millions of years, whether in the form of rainfall or snowmelt. And so you need huge amounts of precipitation for long periods of time to be able to form these. And the only problem with this is that these were formed about almost 4 billion years ago, so almost exactly 3.7 billion years ago or earlier. And so the problem with this is that the sun was even weaker than it was now at that time. So it was about 25% weaker. And also Mars is further away than the Earth. And so at that time, you would have an extremely weak sun, and there's just no way that climate modelers can actually recreate this amount of liquid water on the surface of Mars. So even though geologists and geomorphologists are quite certain that it must have looked something like this, essentially climate modelers tell us, well, there's just no way, no matter how many knobs we turn in our climate models, Mars is just too cold, it's too far away, and the atmosphere that we see now, it's CO2 dominant. There's just no way that we can just pump in enough pressure to make this temperature scenario happen. We just can't do it. And so that's what gives rise to this sort of early Mars climate paradox, right? And so we have the geomorphologists and the geologists who say, well, at this point in time, about 3.7 billion years ago, there has to be huge amounts of fluvial activity. So this is the time we call the Noachian / the Hesperian period. But climate modelers basically say, well, how we can't generate that. So we need to find a consensus. We need to meet in the middle. And importantly, the only solution to this is to find a climate regime that satisfies both paleoclimate models and geological observations. And that's really hard. And so that's why, a lot of people talk about this paradox that we have on Mars, and they say, it is kind of a war and we're always butting heads. And sometimes if you do go to some of our sessions and conferences, there is a bit of shouting and grabbing of microphones. But generally, that's not what it is. It is, it is working together and trying to use each other's constraints to better understand Mars. And that's how it should be. And so in general, people do work together in the field. And more importantly, we need to find better ways to fix this. So we've made good progress in the last few decades, but there's a lot that can still be done. And so the main way we need to fix this is to find better constraints, better geological and geomorphological constraints that are actually quantitative and that modelers can take and be like, oh, okay, so this river must mean there was this much precipitation or whatever, things that they can actually use to refine their model or test their models. And so that's what's really lacking, and that's where we really need to work on. For example, these valley networks that you see here, they were carved over huge amounts of geological time. And so people have used them to find out the total amount of cumulative water that has cycled through them. So they say, oh, you need a water column of 5 kilometers to build these. But that's not really useful for climate modelers, because climate models aren't really integrated over geological time. They're kind of like a snapshot of what's going on given a few dynamic properties and parameters. Whereas some people instead, some geomorphologists will take these deltas and these channels that flow over these depositional systems and say, oh, to form this shape, you need to have a peak runoff or an instantaneous discharge that is this much, at this rate. But also that's not quite useful for paleoclimate modelers either, because they don't really look at peak or instantaneous processes that happen over seconds or days. And, they're more looking at years to a few centuries or thousands of years. So it's we need to find some sort of intermediate which climate modelers can use, which is where this study that I'm going to talk to you about comes in. And so this region specifically here that I've shown you before is Arabia Terra on Mars. It's a very typical sort of mid-latitude location, which is completely covered in these valley networks that I've shown you before. So these eroded valleys here, and they all feed into these sort of lakes. And actually on Mars, what happens is that you've got so many craters, just like the moon, but you have a lot of rivers that flow in, and this is where the water would have ponded. So we call these craters paleolakes because they used to host these huge lakes. And so what we do in the study is to use this relationship, use these geomorphological features we see to try and constrain the amount of water that covered the surface of Mars. And so you can see here an outline of these lakes. And what we're trying to tackle is essentially how much precipitation did you need to actually fill these up? And so the question we're answering here is, what was the intensity and duration of a favorable climate event on Mars? And so for the first part of this talk, I'm going to focus on the first sub-question. So, the intensity aspect of it, how much precipitation was there? And with that, we're broadly going to follow structure where I'm going to take you through these two techniques. First, we map the paleolakes, and then we calculate these hydrological balances. And then I'll show you how we can use that to calculate what P or precipitation was as a function of space. So let's look at how we can answer this question. First thing I'm going to do is to break things down a little bit. I'm going to do this using a really simple and maybe a bit silly analogy, but it's really useful for wrapping your head around the geomorphological climate record on Mars, and also broadly explaining the methodology of this latest project. And so I guess imagine you own this big piece of land. Maybe you're a farmer and you want to find out how much precipitation there is during a wet season in your land. So you don't have much to work with. Actually, all you have in your shed is a bunch of bathtubs for some reason. Bathtubs of all shapes and sizes. So what you decide to do is to distribute these bathtubs across your field with the idea that they can maybe be used to collect water and measure it somehow. The only problem is you're going to be gone for a long time. So maybe you're taking, billion-year long vacation. You're going to be gone for a long time, but essentially you're fairly certain that by the time you come back, all the water will have evaporated after the wet season. So what can you do? Well, you have one secret weapon, which is this big pile of rubber duckies that came with all of your bathtubs. So what you do, very clever, is you decide to place a single rubber ducky in each bathtub. So something like this. You then go away on your holiday and you come back, and the wet season comes and goes. And so everything is now dry as a bone when you come back. And what you find is that some of the rubber duckies are still inside the bathtub, like these ones. However, some of them, the rubber ducky is outside. And the way you interpret that is that for the duckies that are outside the bath, the precipitation must have been such that the entire bathtub filled up and overflowed, allowing the floating rubber ducky to escape. And conversely, the rubber duckies that are contained tell you that precipitation was not enough for the ducky to escape. So you have this catalog of escaped and non-escaped duckies. So then technically all you have to do is to measure the sizes of these bathtubs, and then you have a technique for figuring out how much precipitation your field gets during a wet season, which is great. But how does this apply to Mars? Well, as it turns out, we're looking at the exact same scenario, except instead of bathtubs and rubber duckies, we instead have these basins and valleys on Mars. And instead of being gone for just an annual wet season on Earth, you're gone for much, much longer, so millions or even billions of years, long after the cessation of Mars's wet climate. So this, for example, is a hydrologically closed basin on Mars, which means that you have valleys that flow in, so you have these inlets here in white, but there are no valleys that flow out of the basin. And we can tell which direction they flow in by looking at the elevation. So these ones decrease in elevation, but there are no valleys that then decrease, once again, leaving the basin. So this is a hydrologically closed basin. However, we also have hydrologically open basins on Mars. And for these, there are not only inlets that flow in, but there are also these outlet canyons that were eroded. And so this happened when the basin filled to the top, overflowed, and that caused a big catastrophic flood that it basically eroded down the rim of the crater and allowed the basin to drain. And so to relate these two scenarios back to our farmer scenario, the presence of an outlet canyon is the scenario where you have an escaped rubber ducky, right? Because that tells us that it filled to the top. Whereas, of course, the contained ducky is our closed basin, like on Mars. So that's what we're dealing with on Mars. And so fortunately on Mars, we have this large database of basins. We have about 100 that are distributed all over Mars that are fed by these valleys. And about half of them are open and half of them are closed. And so essentially by simply measuring their morphologies, we can combine this with what we term our hydrological balances that I'll talk about later to calculate what the amount of precipitation was during a Mars ancient wet season, whatever that is. And so for this, we need three key measurements. We need the lake area, the watershed area, and the lake volume. So these are broadly shown here. And so one important thing to note is that for open basin lakes that you can see here, this volume of the basin that we're measuring is a minimum volume of water. And the reason for that is that this is a minimum amount of water you need to be able to overflow, just like in the bathtub. Whereas in closed basin lakes, this volume of the basin that we're measuring is actually a maximum, right? Because we know that the lake never actually filled up, it never overflowed because we don't see an outlet canyon. So the rubber ducky didn't escape. So closed basin lakes are maximum volume permitted. Open basin lakes are a minimum volume that you need to be able to fill it. So now I'm going to take you through our hydrological balances to see how we can actually derive an expression for precipitation using the measurements that I've just shown you we've made. And so when I use the term hydrological balance, all this refers to is a standard set of conservation equations from a field term limnology that looks at how lakes change. That essentially these equations just represent the amount of water that enters and leaves a bounded hydrological system, whether it's a bathtub or a Mars basin. And so in a very simplified system, we have some precipitation which is incident on a lake, and also its contributing watershed. And so we assume that the water is flowing on the surface here and following the topography and entering the lake system here. And so that means we can express the lake filling rate, or QL, very simply as the precipitation rate times the area, this combined area here. However, we're interested more in the total amounts, not these instantaneous rates. So what we do is to integrate this expression over some large time period. So imagine, there's some time t for all of this to happen in, which we call a runoff episode, which is equivalent to something like the duration of a wet season. And so doing that gives us this expression, which is very similar. And all it's saying now is that, well, the total lake volume is equal to the total precipitation, which is in some sort of length, like meters, times the combined area again. So this area here. And this term PT is what we want to solve for, the total precipitation. And one important process we haven't mentioned, though, is, of course, evaporation. And so this could actually cause significant losses and change our expression a bit to something like this. So to first be able to solve for this PT, we need to figure out how we can constrain the evaporation in the first place. So how much of this water are we actually losing? And so one way that we can approach these losses through evaporation is to look at what limits are actually provided by the lake basin morphologies themselves. So what we can do is we can take that earlier expression and very simply just rearrange it so that now we have evaporation as a function of precipitation that you can see here. So that means that for each individual lake, each basin, whether it's open or closed, will now have its own EP function. And so if we plot these, so here we have evaporation as a function of precipitation. That means that now we can plug in values for each lake into these functions and we get a different line for each lake. So when we plot that, it looks something like this. So these are almost 100 lines for the 100 lakes we have. And for the blue lines, these are the open basin lakes. The red lines are the closed basin lakes. But, well, there's one thing I need to mention first. Yes, I have talked about this. And so you need to remember now that for the open basin lakes, remember that what we had was a minimum volume, right? So what that means is that this line is actually a maximum permitted value. So only values that are below each of these lines are actually permitted. So evaporation, precipitation values. Whereas for the closed basin lakes, remember that that's a maximum volume for the lake. So actually this line becomes a minimum. So only values above this are permitted. So all that happens is that because this is a minimum or maximum, it changes this into an inequality like you can see here. So only things below this line or above this line are permitted. But now how can we use this to give us the permitted evaporation total? Well, one way to evaluate this is by using something called the aridity index. And so the aridity index is quite simply the ratio of precipitation and evaporation. So it's just P over E. And because this is a log-log plot, essentially any aridity index value is just going to plot as a straight line with a slope of 1 here on this plot. So let's just take two standard aridity indices on Earth. If you're in a hyper-arid environment on Earth, you have an aridity index of 0.5 or less. So this is a hyper-arid environment. The higher up you go, it would be more arid. And a humid environment on Earth would be this humid line that you can see here. So an aridity index of 0.75 or more. And so what we then do is to find the most arid scenario, or in other words, what is the lowest aridity index that allows for all of these open basin lakes to still exist on Mars? And the answer to that is given by this lowermost open basin lake, which is in this dark blue line here. And so essentially, if you think about it, it can't be more arid than this, because then these open basin lakes wouldn't be able to exist. So for example, if it was hyper arid on Mars, this gray line here, none of these open basin lakes here could actually exist. So this is the most arid it can be on Mars, this black dotted line, for all of these to exist. And so that's all we're saying. And so this value here, this AIM, which is this minimum aridity index on Mars, is about 0.26, which corresponds to a sort of semi-arid environment on Earth. But then if we try and look at what is the most humid scenario that's permitted, well, actually there's no constraint on that. So you could have an infinitely humid environment and it would still allow for all of these basins to exist here. So we've got a range from anything between a 0.26 aridity to infinitely humid. So that's what we can gather from these morphologies. And so what we can then do is feed this aridity index spectrum back into our original equations to inform these hydrological balances, and specifically inform E here. So for example, we've got this range of AI values, and we know that E is essentially just P divided by AI now, and we can just plug that in. But then one thing I need to remind you is that we've got these two N spectrum scenarios. So remember that for the open basin lakes, we have a minimum volume. So that means that if we want to calculate the precipitation, we're only going to be able to calculate a minimum precipitation that was able to flow into these basins. For the closed basin lakes, it's the same thing. So we have a maximum volume, which means we can only calculate a maximum precipitation. And so to push the minimums to being even more conservative and the maximums to being even more liberal, what we do is we feed in this most humid scenario into this expression and the most arid scenario into the closed basin lake expression. And so that really pushes our boundaries out into what is allowed on Mars. And that would look something like this. So in the most humid scenario, infinite aridity index just means there's no evaporation, zero evaporation. It's not very likely. But for this most arid, we plug in that AIM value that we have. And so we, in the end, get these two final expressions, which allow us to calculate the minimum and maximum precipitation for each lake, depending on whether it's open or closed. And so what do the results look like for this? Well, one way to look at these results is by using a frequency distribution plot. So for example, here in the x-axis, we have the local precipitation calculated for each system. And in the y-axis, we have the number of lakes in each bin. And so remember here that when we talk about precipitation or PT, it's basically a time integrated precipitation depth in something like meters over basically quasi-continuous runoff episode. And so something we notice immediately is that the open basin lakes and the closed basin lakes have sort of distinct distributions, right, with a very small amount of overlap. And so this shows that our values are self-consistent because remember, open basin lakes give us a minimum amount of precipitation and closed basin lakes give us a maximum. So what we're saying is that generally minimum is around 4 meters of precipitation that you need for each of these basins, whereas for the closed basin lakes, the maximum is about 159. So that gives us these sort of defined broad bounds on the amount of water that's supplied to the Martian surface during some wet episode or runoff episode at a global scale. And importantly, these lakes are distributed across the entire planet. So what we end up with is this spatial distribution of permitted evaporation. So where you have minimums here and maximums here. And so you can see here, there's more runoff for some of these, whereas here in the drier ones, there's less runoff, so it's limited. And one of the key implications is that we now finally have these local values which can be tested against the outputs for global climate models. And this gives very specific quantitative constraints that models need to satisfy to be able to align with the geological record that we can see here. And so that sort of answers our first sub-question, looking at the intensity of the climate. So how much water was there? And this is something that we've just published recently. So the paper was put online last summer, I think. And so you can read more about that if you want. There's a few more figures and we go into deeper explanations on all of that. But what I wanted to do for the next part of the talk is to focus on the temporal aspect. So, how long did it actually take? What is that runoff episode? And so again, the structure is briefly shown here. So instead of isolating P, we now want to look at what is T, what is that runoff episode duration, and how does that vary over space? And again, the way we're going to do this is by taking these geological constraints again and looking at taking some climate model data to inform our results. And so remember I showed you that we have this big database of lakes, and then we have these open and closed basin lakes, but there is also a third type of lake basin that I didn't mention, but it's a new one that we identified and classified, which is termed a coupled lake system. And these are really interesting because essentially what you have, this is shown schematically here, is you have an open basin lake fed by these lake inlets, which has an outlet which directly feeds into a closed basin lake, which is just downstream of it, which also has its own inlets. And so here's an example of one in real life, what this looks like. So you have here the inlets flowing into this open basin lake. It sort of breaches and flows into this closed basin lake, which has its own valleys. And so these are really interesting because, these lakes are not too dissimilar in size, but but one of them overflows and one of them doesn't. So they're really curious features. And so remember, in the previous work, we looked at the hydrological balances of these lake systems to find the distribution of precipitation, PT. However, I'm just showing you that for these coupled systems, these circles in white, we not only get a minimum, but we also get a maximum because we've got both an open basin lake and a closed basin lake that are hydrologically connected. And so that's really interesting that you get these bounds here as well. So we only have about 7 of these though, so they're not that common, sadly. But what I am going to do next is to delve deeper into this concept of a runoff episode and, try and figure out what is this value T, which thus far we've sort of said it's indeterminate, and how can we explore ways of actually defining T. So first of all, when we talk about runoff or PT during an episode T, I just want to remind you that we're not talking about peak runoff. So we're not talking about that one day of flooding over a year. And we're also not talking about the cumulative runoff over the entirety of the lake lifetime from the moment it was formed until, millions of years later. But simply, we're looking at the amount that's fed into lakes during a single sort of continuous episode. And so another way to think about this is to look at it graphically. So imagine that we have some oscillating climate on Mars. So on Mars, there's rain, there's no rain, there's rain, there's no rain, something like this, where, you have runoff at 0, and there's these discrete events that produce rain on Mars, which is something like you would expect from the way that Mars sort of has a tilt. And so if the events are not long enough or intense enough, they will never cause an open basin lake to breach. However, if there's a single event that is either long or intense enough, this will actually cause the open basin lake to breach. And it's this threshold event, that breaching, that characterizes the total minimum precipitation depth for that runoff episode. So that's really what we're measuring. And so this time period here is what we define as our runoff episode T. And note that this doesn't actually provide any information on the events that happened before or after this event. And so for closed basin lakes, the idea is similar, but in this scenario, there's, again, never any event that is intense or long enough ever to breach a closed basin lake. And so this also gives us information about the maximum amount of PT, or precipitation, that could have occurred, again, over some time T. And so interestingly, for a coupled system, which contains both an open basin lake and a closed basin lake, we know that T and PT is the same. So they get the same precipitation. They should be forming over the same amount of time. But because they're hydrologically connected and spatially and temporally coincident, we can use this to try and investigate their hydrology and their timescales in more depth. So that's where their value really lies. And so again, this is the same example of a coupled system I showed you before. One way to look at this is to examine how lake volumes in both lakes inside a coupled system vary over time. So how does this V value change as a function of time? So I won't delve back into the maths of how this happens, so don't worry. I'm just going to show it to you graphically. It's faster and more interesting this way. But imagine that you have time in the x-axis. So this is an absolute time. It's a sort of relative time. So let's say that at 1, a breach occurs in the open basin lake. So this is just sort of dimensionalized so that at 1, that's where the breach happens. And then here on the y-axis, you've got the volumes of the 2 different lakes. So how do these lakes look over time? Well, it looks something like this, and I'll take you through these lines. So the open basin lake, essentially, before breaching, it will start to fill up proportional to its watershed. So it's just filling up because it's being fed by these inlets, as you can see here. And the closed basin lake is also just filling up at some rate proportional to its own watershed. However, once the open basin lake reaches its maximum volume, which can actually be held by the basin, it breaches. And so when that happens, it loses water because it sort of forms a canyon that erodes the rim down and allows water to escape. And so this escaped or drained water is then directly transferred to the downstream closed basin lake. So if you imagine it sort of erodes a bit of a canyon here, all of that water at the top will then flow down into the closed basin lake. So it this volume here is the same as this volume here. It's just transferred downstream. However, after that, the open basin lake volume essentially doesn't change. So it just kind of stays the same, stops eroding after this catastrophic event. However, now the closed basin lake has captured both of these watersheds. So these are all connected, and everything that flows in here flows into the closed basin lake. So now the closed basin lake is increasing at a much faster rate. However, the runoff and the precipitation can't continue forever, right? Remember, it's limited by the actual size of the closed basin lake here. And so we know that the closed basin lake never overflowed. There's no evidence of a canyon. So there's this limit here to how much it can actually flow, and that's limited by its volume. So what we end up with is this defined range of permitted timescales, which tells us that runoff had to be a discrete event. So it had to be enough to make this breach, but it certainly had to stop here before the closed basin lake overflowed. And so for this specific example here, this coupled system, the permitted runoff episode can only continue for about 44% of the time it actually took to fill in the first place. So if you imagine kind of like a tap, you turn it on, you fill your cup, you overflow, and then you very soon have to turn that off. So, you know, for a lot of people, they think that Mars was kind of always precipitating a little bit, but this really shows that no, you really do have to stop soon after you breach some of these, which is an interesting result. And so aside from being interesting in their own, these relative timescales, you know, they give us an idea with regards to filling and breaching and lake lifetimes, but how can we go about actually quantifying the duration of a runoff episode? You know, looking at it, how many years are we talking? So here I show a simple way that we can tackle this. Firstly, we have our local precipitation, PT. So we know the amount of precipitation in meters, for example, that each couple system needs, and we have a minimum and a maximum. And second, another constraint we have is actual precipitation rates derived from these global climate models on Mars. This one, for example, is from Robin Wordsworth's work in 2015. And essentially, he creates this climate model, which tells us what is the possible spatial distribution of rainfall on Mars, given some parameters. And so this is in meters per year, for example. And so quite simply, if we have a precipitation total, and if we have a precipitation rate, then by doing very simple maths, we can use these two to solve for a time scale t, simply by taking the total precipitation divided by the rate, you get an episode time scale in years, and that's what we're going to solve for here. And so suppose we have this global distribution of precipitation, such as this one. It's the same one, but slightly different color. Remember that is actually, well, you can't remember because I haven't told you, but on Mars, there are actually several different global climate models because there's lots of things that you can tweak, but these are other models from other authors that, you know, use different atmospheric pressures, use different tilt axes on Mars. They give different inventories of water. So you can really change, as you can see, quite drastically how much rainfall you create on Mars. And so we decided to take into account all of these. So try and see, you know, what timescales do we get for all of these different scenarios. But just to show you as well, the way we calculate this for each system. So this one here is that perspective view of a coupled system I showed you before. So that's this small one here. And so essentially we take the climate model for each one of these and we just calculate what is the average precipitation rate that you would expect in the whole system here. So for this one that we saw before, precipitation rate of about 0.5 meter a year is what you would expect from this model. And so going back to this first, you know, I'm going to talk through them one by one, but first we'll talk through Wordsworth's model. Well, we now have basins that have a total precipitation each and also a model average runoff rates. However, we know that there is a range of permitted timescales for each of these, like I showed you. And so remember that we have 7 coupled systems that are shown here in black. And for each coupled system, again, depending on their lake morphologies, we'll have a different version of this plot. So we'll have different ranges of permitted timescales. And so we have a total of 7. And so schematically, it would look something like this, you know, depending on their shapes and sizes. Some will allow to be much more, some will be tighter constrained. But they all have these different permitted timescales. And so what we do is to build a histogram for all the permitted timescales given the runoff rates from these models. And so what that looks like, building this histogram, is something like this. So I'll just take you through this really quickly. So you can see here in the x-axis, that's the actual duration of the episode, that how long it takes to actually fill these up. So this time here. And the y-axis tells us how many of all of the 7 coupled systems that we have, you can see 7 total here, how many of these systems are actually satisfied by this time. So for example, here, a runoff episode duration of 10 years only satisfies one of the coupled systems. So only one of them, so it would be at the edge here. So only one of them actually is happy with that time scale. So that's not a very good time scale estimation, probably. However, a sort of time bin between 100 to 200 years actually satisfies 5 of the 7 systems. So what that means is that that's probably the most permissible or the most probable time bin. So for this model here, we'd say that, all right, 100 to 200 years is, it's pretty good at satisfying these systems. And that's probably how long it took if we think that the runoff rates from this model are correct. And so we can not only do this for a single scenario, but for multiple climate scenarios. So for example, Robin Wordsworth, he looked at not only rain, but also what would be the runoff rates for snow as precipitation of snow. And so that gives a different map of rates, and we use those to calculate, again, different timescales. And so you can see here that you have these sort of faster timescales, as you would expect, because usually when it's warmer, there's a lot more rain, colder, a bit less snow deposition, so this takes much longer. And also you get more coupled systems satisfied here and less for the snow, or you have a broader distribution for snow. You need more different timescales to be able to satisfy that. And not only can you look at different models, but at different scenarios, you can also look at completely different models from different authors. So Kamada, for example, looked at how does the atmospheric pressure change the runoff rates. We calculated those and saw that, as you increase from 0.5 bars, so half what we see on Earth, you sort of start to increase runoff rate, which means you decrease these episode durations, but then it kind of reverses again. And that's actually because if you pump in too much atmosphere into Mars, CO2 atmosphere, you actually start to form clouds, and then clouds reflect back, like the albedo gets higher. So you actually start cooling it if you put in too much atmosphere, which is interesting to see that too in the timescales. And then Scott Guzerich looks at how, what is the water inventory, the initial water in the model actually change. So you have 10 meters or half a kilometer, that doesn't change it too much. And then Catherine looks at actually generating atmospheres from impact. So what she does is essentially make this huge impact, cause enormous amounts of heating and a thick atmosphere, and delivers all these gases onto Mars. And what do these runoff rates look like when it starts raining? And so we can see that there's not much change, but generally they're a bit faster. The episodes are shorter than what we've seen before. So these are huge impacts, about 100 kilometers in size, that would cause this. But so, I mean, this is what they would all look like together, just to show you the broad distribution of all the models we have so far. And I don't have too much time to talk about all of these individually, of course. I just wanted to point out some key observations that we see. And the first that you'll notice is that the most permissible timescales generally lie between 100 to 10,000 years, broadly, and a bit less than that, for a single runoff episode. And so remember that the valleys that feed these lakes are quite deep, so you'd probably need several of these episodes to actually be able to carve the valleys that go into them. So it's not just one 100-year episode, it would have to be maybe hundreds or thousands of these. So this is really important for understanding how many episodes and how much time you would need to actually generate these systems on Mars. And second is that there's no single time scale that satisfies all of the systems, right? So the maximum we get actually for all of them is that only 5 out of the 7 coupled systems are satisfied, which is still a good and important achievement. It just could mean that there wasn't a single episode value. So they all weren't formed in the same sort of episode duration, or they occurred in different episodes or in episodes of different durations, or also it could mean that there's just more space to explore different and more climate models which look at different parameters and maybe could even satisfy more systems. And so I'll just jump into the key results from this. So we looked at paleolakes first, which provided these spatial constraints on precipitation. So we looked at they could probably be somewhere between 4 meters to 159 meters, just looking at their shapes. We can also see from their shapes that, these episodes for which there was runoff, they were actually very defined and bounded by how much you can actually continue to precipitate because of the fact that closed basin lakes just don't breach. And so what we did here was to integrate and sort of combine model data with geological data to shed light into these episode timescales and see how they vary for different scenarios. And so we get this interesting sort of range of timescales. And then fourth, this has, like I said before, very important implications for testing climate models on early Mars. And this is going to be really important going forward and trying to understand what is actually important, what is needed to generate these systems. And then the fifth and final thing I wanted to talk about, which is important again, going forward and looking at, what's next is these, looking at these independent constraints. So, one of the problems in planetary science is that you're not there, there's, I came up with this sort of order of magnitude constraint for timescales, but how can we figure out whether that's true? And the only way to advance planetary sciences is to get ground truth, right? To actually have access to the locations you're studying. Of course, for planetary sciences, that's hard. And so one thing that we do, which I'm going to focus on a lot as well, and a lot of planetary science do, is to do field work in terrestrial analogs. So places on Earth that are very similar to Mars. There's different places for this. So depending whether you're studying the geochemistry or fluvial erosion, or if you're studying volcanism, there's different places on Mars that are good for that. If you're more interested in dunes and formation of desert systems, of course, the Atacama Desert. But for me, one of the places I've worked in is Iceland. So this is actually a crater lake in Iceland that I went to in 2017. And so we did a lot of work there looking at erosion rates and how do these basaltic landscapes, which is the same sort of landscape, same sort of lithology as Mars, how do they erode? How long does it take to actually carve some of these canyons? And that's what I'm going to be working in for the next few years when COVID goes away, obviously, because we have to be able to travel. And so the second thing, of course, is space missions. And, it's very exciting. I think Perseverance rover is actually landing in almost exactly a week or something today. And so this is going to be absolutely critical for informing some of these, testing these hypotheses, informing our results, because what we're doing is we're actually landing in one of the open basin lakes that are contained in this database, and which is Jezero crater. So that's that delta that I showed you before. So it's this gorgeous delta, which really must suggest that there was significant amount of water ponded on the surface of Mars for a long time. And so it'll be really interesting to actually be able to probe this and see, what were the lake levels? How long were they there for? Did they oscillate? What is the extent of this deltaic system? Can we see evidence for biosignatures? So ultimately, if you've got a place like this is just a recreation of the lake system in Jezero Delta, you could be able to host life. I mean, this was probably around the same time on Earth that we developed life. So it'll be really interesting to see what sorts of data we get from Perseverance in the next few years. And it's going to be really, really important for Mars geomorphologic studies in the next decade. So I'm really excited about that. And I guess with that, that's all I had. And so, please let me know if you have any questions and I'll be happy to answer them.
Do you think with water, it means you may find chance to find life on Mars?
Life on Mars today would be very difficult. The reason for that is, it wouldn't be life as we know it. The problem is that Mars doesn't have an atmosphere like Earth. And so you just wouldn't be able to actually have the organic molecules and the even biosignatures preserved. So anything that is on the surface of Mars would probably be blasted with radiation. So there's none of it now, but that doesn't mean that deeper down in the crust or a few meters on Mars, there couldn't be some ancient life that is still preserved, but it certainly wouldn't be able to be active and be metabolizing and working now. It's just too much of a cold, hostile environment with nothing to be able to sort of keep it going, and certainly not enough energy. So, I mean, you could have evidence for it preserved. That's what we're hoping to see. If anything, it would still be interesting if it's not there, because it means it's more rare than we thought. It's all of the outcomes would be interesting in some way.
Do you see any evidence for the multiple episodes that you said might have happened? Like, do you?
Absolutely. So the evidence for that comes from several different locations. So for example, geochemists on Earth, I always talk about geomorphologists and climate scientists, and then the geochemists get really sad and angry because we always never mention them, but there's a huge body of geochemical work done on Mars as well. And so they do see as well that there are lots of deposits that are, some are more arid than others. So you've got these sulfates and you've got these clays, and a lot of time you've got clays and things with less clay that suggest that there were repeated episodes of very wet timescales and less wet timescales. So you do see this in the geochemistry as well. Not only that, but in a lot of these systems, you sort of also see this layering, which suggests abrupt ending in the sedimentation. You see it as well in the morphology of the valleys, which, when you look at like the profiles of a lot of these rivers, they look more like very arid channels that form in places on Earth where there's very sort of extreme storms and then nothing in between. And so generally, I think, a very sort of episodic and punctuated history of the paleoclimate is very much supported by all sides. I think the fight is more whether, how long did this last for? How long were the actual episodes? But I think everyone broadly agrees with that. And one of the reasons too is that on Mars, it's a bit simpler than Earth in many ways, but a lot of climate scientists and geologists believe that, you have the tilt axis on Mars, which varies a lot, much more than the one on Earth. So it can be anything like 60 degrees to 0 degrees. And so many scientists believe that probably that dictated the episode. So when you've got the obliquely turning, you'd kind of, all the ice in the poles would go into the atmosphere, and then that would rain down, and then you've had this sort of oscillating climate that could be the reason why you have these episodes. So that's one of the explanations we have for it, but there's still other explanations that we're looking at as well.
What time period did you say this was occurring? About 3 billion years ago?
Yeah, so it happened all the way up to 3.7 billion years ago.
And when was that? Is there any correlation with that and the time period in which we had heavy bombardment?
Yeah, so the kind of in some ways. So we had the late heavy bombardment a bit earlier than that, and it was trailing off before then. And so we do use the cratering record and late heavy bombardment to inform our cratering. So, the reason why we know the ages of surfaces on Mars is because we have a good understanding of that, the behavior of the bombardment in the solar system.
So at this point, there's no correlation between the radiation and or elements like iridium that could be attributing to the climate, warmer climate time periods?
Not that I know of. A lot of scientists have looked at the possibility of triggering these environments through impacts. If anything, Catherine Steakley that I mentioned in one of the climate models suggested that maybe you could actually deliver hydrogen through a lot of these impacts and these really large impacts at that time. And that could be a way. So if you've got 100 impacts of 100-kilometer radius, you could probably inject enough hydrogen to be able to sustain an atmosphere. But even then, it's not quite enough, because you do need, in the end, you need millions of years of water to carve the channels. And there's just, when there is an impact, it's just not enough, because you can generate a climate for about 10 years from some of the more recent models. And so even if you do that 100 times, that's just not quite enough.
when you do a climate model here, it depends not only on energy input and heat loss and that, but also on the transfer of heat and the involvement, location of bodies of water and continental land masses and the transfer of heat in the ocean and all that. How does a climate model work on Mars where we don't really, in this, see any evidence for large oceanic bodies of water?
Yeah, of course, that's a really good question. And there will be some scientists that would disagree with you. Not me, but there are some that are very convinced that actually, I don't know how much you know about the topography of Mars. I actually don't have any good images of it, but if you look at the topography of Mars, the northern hemisphere is very different to the southern hemisphere. The northern hemisphere is very smooth, it's very young, whereas the southern hemisphere, for some reason, is much older and cratered and rough. And so many geologists have proposed that actually the northern hemisphere was a giant ocean. And so, different people have looked at different levels, like, it could have been up to here, it could have been a 3-kilometer high ocean, a 4-kilometer high ocean, or half a kilometer. And so some would argue that there is evidence for a large ocean, but it is very contested, and I wouldn't say that everyone agrees with that. And so when people like Robin Wordsworth do generate these climate models, for the case of rainfall, I think they're only able to actually make rainfall if you do have a large liquid body of water in the northern hemisphere. And some of them don't do this. Some of them just maybe put some in the lakes. So it varies per model, but a lot of them do try and add this and see how that changes. And I think Scott, the one who looks at different water inventories, I guess just does different levels of how much water and how much of the ocean is actually there. But, some suggest that this is like a shoreline. There are a lot of channels that flow into it and then some deltas, but it's not really continuous. It's all at different elevations. So it's a bit confusing still, if that really was the case.
When you look at different atmospheric pressures, you talked about the pressure of CO2, and is there any thought of other gases in the atmosphere that have since been lost other than water?
Yeah, I mean, there would have been minor amounts. CO2 has to be, the current atmosphere is CO2 dominated. So, me not understanding much about atmospheric dynamics, it just means that CO2 has to always be the dominant species on Mars. But a lot of people look at, well, what if we add some methane? Can that change? Can that help? What if we add hydrogen? What if we add sulfur? So some people suggest, well, what if it was sort of generated through volcanism? And there's this huge volcano on Mars, which is the largest volcano in the entire solar system. It's like 22 kilometers high. It's enormous. And so could that not have supplied enough sulfur and hydrogen to keep a thick atmosphere going? And again, the answer is no, not quite. And so, it has to be CO2 dominated, but even injecting other species, it doesn't quite add up yet. But yeah, I think people are looking at hydrogen now as more of one of the options, one of the main options, but people still look at methane as well. I'd say hydrogen and methane are the two ones that are most commonly incorporated into models of Mars.
How does your model account for the salinity of the water? Because I would assume like the closed lake system will have build up salt because it's not, it's just evaporating water. It's not collecting. It's not running off water, so it's a higher salinity, whereas the open lake is going to be naturally refreshed. But then also if there's any salt deposits that are changing the depth of the lake.
Yeah, absolutely. That's a good question. And I do think that a lot of water, so a lot of gully systems that we see today on Mars, some people suggest that it could be through salinity that you can actually generate these today very short amounts of liquid water flowing on the surface of Mars. So I do think salinity would play a big part. And that's also something we're hoping to explore when we go to Jezero crater and with Perseverance rover. And we're hoping that we can see some more in detail evidence of salinity, because that'll help a lot with looking at timescales of alteration. But with regards to the model, generally with the hydrological balance, I mean, the water that flows in would not have salt. And so the water that evaporates would not have salt either. And all of the sort of solids, I mean, the sediment is deposited at the bottom too. And so if you think about it, the volume that we're measuring actually doesn't take into account that, well, doesn't really care about all the sediment that is deposited. And if there is salt deposits, they're also here. So really, when we do measure this basin volume, it's only really the water volume that would have existed on top of any sort of solutes or sediments. So it wouldn't affect the calculations at all, because really it is in the end a water balance, because the water goes in, water evaporates out, and then this is the only space available for water itself.
But that would be the volume at the last occurrence of water. But if you have water that's happening over millions of years, the lake's going to be deeper, and then it's going to start filling up with sediment or salt deposits. So that your volume is changing, your maximum and minimum volumes are changing.
Yeah, that is true. That is true. So you could get a cumulative sort of salt deposit that would actually take away from the volume. That would be interesting then to see how that's a really good question, and I haven't thought about that in that way, what the cumulative salt volume could contribute in terms of loss of mass when we're measuring that volume. That would be interesting to see, because I know that other things like, for example, a lot of these are draped with aeolian and sand dunes. And we know that on Mars, really the maximum amount of sort of aeolian and dust cover that you get is about 20 meters. And so when you consider that, you know, these basins are already 200 meters, so maybe, okay, 10% off for drape, which we calculated some of our uncertainty. So it would be interesting to see if you would expect the salinity to generate more, like enough to actually, you know, make the uncertainties even larger than that. I actually can't think off the top of my head how much it would be, but I would expect it to not be a huge percentage off from where it is. But again, these are order of magnitude estimates. Right. So yeah.
And plus your evaporation rates will be different between the open and the closed lake.
Yeah.
High salinity, it's going to evaporate slower.
Absolutely.
Kind of like the Dead Sea, I guess, or Salt Lake City. Salt Lake.
Absolutely. No, that's a really good point. It would be interesting to look at that for sure.
Where is all the water that was there at one time?
Good question. It has probably escaped. Well, it has escaped. Some of it is in the crust, and it's sort of frozen and sort of aquifers in the crust, but a lot of it has escaped. And the reason for that is that early Mars was very similar to early Earth in that they probably had some form of like a molten core and some tectonics. Nothing, we don't really see evidence for too much, you know, actual plate tectonics, but it probably had something, because we do see these big rifts and things on Mars. But the problem is that Mars is so much smaller than Earth, so it couldn't actually maintain and generate its own dynamo, its own sort of fluid core and tectonics. So very early on in this time, it actually froze and kind of, you know, broke down. And so what happens is that if you don't have a molten core like we do on Earth, we have this iron, which is basically slushing away, which is what generates our magnetic field. And so on Mars, if you shut down this dynamo, you then shut down the magnetic field, and you basically lose your protection from things like solar wind. And so since then, since the dynamo shut, which was very, very early on, you know, close to the time where valley networks were happening, and when they shut down too, probably not a coincidence, that is the time when you basically, Mars lost its shield and everything began to be stripped away. And so
I was gonna ask that. So right when the magnetic field was lost, it would have been sort of like a pretty quick process then to lose everything. And then all the weather or whatever you want to call it would be gone.
Yeah, absolutely. So we know that certainly the valley networks was a very it was a fast process, that they were happening a lot and they stopped happening because all of them around the world kind of stopped happening around their world, stopped happening at the same time. And again, the dynamo shut down at a similar amount of time. But I do think that people predict, scientists predict that the losses wouldn't be that drastic. And for example, you can actually measure the hydrogen ratios. So you can look at the isotope deuterium to hydrogen ratios on the atmosphere of Mars today to get it. You can actually measure it to find out what the loss to space is of water. And what I do know is that a lot of it doesn't line up. So what we think it should have lost to water doesn't line up with how much water we say there has to be and how long ago it lost. So we do know that something happened then, but right now the maths doesn't really line up for what we can measure now from the atmosphere and what we see in the geological record and what happened tectonically. So there's a little bit of alignment that needs to be done there too.
Question for you. When it comes to your time frame on Mars, are we talking about like 1.5 billion years of Mars existence even before this time period where you're at?
So Mars would have been formed at a very similar time to Earth, so something like very close to 4.5 billion years ago. So yeah, 4.5 to 3.7 would be less than 1 billion years.
Okay.
So yeah, so about 800 million years, something like that. Still quite a lot of time though for things to happen.
Is there any clues with Martian meteorites in terms of in your area?
In terms of what?
Maybe? Like maybe with zircons? I don't know if they found zircons in Martian meteorites, but.
Oh, actually, I don't know about that. That's a good question. I know that they found, you know, it's hard with a lot of these meteorites, but they found things, you know, shapes that they've suggested could be organic molecules. They found things that morphologically speaking look like biological activity, but I don't know specifically about zircons and what they've been able to do with Martian meteorites. That's a good question. I'm not a meteorite person and I rarely work with them, but yeah, I wouldn't be able to answer that question.
Okay, thank you.
Mm-hmm.
So given that the sun was, you said 25% smaller.
Weaker.
3.5 billion, weaker.
Mm-hmm.
Okay, not smaller, weaker. Well, I think it is expanding as it gets older, but that's not the point. So Mars could have been quite a bit colder. Is there any possibility that what was flowing was not liquid water, but was liquid methane?
So the problem with the thing is to have a liquid on Mars that is able to do all of these things. So you have to have a liquid that is, you know, close to its triple point at the broad range of temperatures we have here. Not only that, you have to have a liquid that is exists in enough quantities in the solar system in this location, and you also need a liquid that is able to actually erode valleys. And so something like methane, it's not quite cold enough for methane to be stable. You'd have to have several tens of kelvins colder. So somewhere like Titan, where you have methane rivers, that's perfect for methane. It's very close to its triple point. And the biggest problem is that methane actually wouldn't be able to carve into bedrock. So on Titan, methane is basically the liquid that flows and forms all these rivers, because on Titan, the crust is ice. So when you have methane flowing over ice, the shear stresses and the amount of force you need to carve valleys is very similar to water over earth, over silicate rock or other types of rock. But on essentially methane wouldn't be able to have it doesn't have the density or the ability to carve rock the same way that water does. And so really considering the abundance that there is on the surface of Mars, the range of temperatures, which could, you know, you still could have intermittent heating on Mars, and the fact that this is hard basaltic rock, water is really the only liquid that we know that could do that. But on Titan, of course, methane is the one who's doing all the work, and it's really impressive actually that rivers on somewhere like Titan, which is a moon off of Saturn, rivers look almost exactly the same as they do on Earth and Mars, except they're actively flowing with methane, which is crazy.
Well, fluid dynamics is the same for pretty much all fluids.
Yeah, in terms of the river systems. Yeah. So absolutely. So, you know, we're looking at the, you know, erosion of the riverbed. You can simulate it using the same equations we do in every planet. You just have to be mindful of course, things like gravity, which affect it, of course. And,
sure.
Yeah.
Are there any glacier carved features on Mars?
Yeah, absolutely. That's a really good question. And actually, if you look at the, let's see, the distribution of all of my lakes in my database, you'll see that it doesn't really include. So of course, I told you the northern hemisphere is very smooth and young, so there's not lakes here, but you can see that there's, basically a huge band of latitudes that we don't consider. And the reason for that is that from like 30 degrees southwards, essentially a lot of this region is glaciated. So instead of having nice V-shaped valleys and dendritic valleys with tributaries, you start getting huge signs of glaciation. So more like U-shaped valleys like we see on Earth. So we sort of didn't consider that into our database, of course, because there's a huge glacial signal, and the closer you get to the poles, the stronger it is.
Thank you.
Do you have an estimate of how much of the planet was water covered at any time? These lakes are pretty small compared to.
Absolutely, yeah. You wouldn't actually be able to, almost if you zoom out, all of these are smaller than the icon that you can see here, the little symbol. But for example, there's one which you would be able to see from space. I'm trying to see if you can see it here. I think it's one of these systems here that would be a huge lake. Some people think Hellas was a huge lake that was filled by groundwater. And of course, if the whole hemisphere was an ocean, then that would be visible, I guess. When people make images like this is what they envisage. But if it was like that, it either wasn't always like that, certainly. It was very intermittent, or it also could have been an ice-covered ocean. But, this is the extreme version of what we'd expect on Mars. But for the other ones, like you said, these lakes are small, but, they could also be connected through groundwater. So maybe a lot of the water you wouldn't be able to see. But for some of the larger lakes, you could. So there's a bigger one here. Yeah, and maybe these ones were filled in as well. So who knows? It depends who you ask.
If you consider that the Earth is 70% water covered, you might consider this 10% or 20% max.
Yeah, I would think so. Again, there are people who would say much more. So I guess if there are people who would go as high as probably 40%, but I would probably be more on the conservative side and say 10% from the lakes at most.
People also talk a lot about, is there potential for life on Mars and that sort of thing. Is there a kind of a carbon balance? You have to, for practical purposes, have carbon. If you're talking about carbon dioxide, that's in the atmosphere. Granted, there's a fair bit of atmosphere, but you essentially, to have life, you have to have one animal eating another animal, be it big or little. It doesn't strike me that you could have life on Mars, even though you have water.
True. So there are actually big carbonate deposits on the surface of Mars. So this delta deposit here on Jezero, actually huge chunks of this are carbonate deposits. So it's not that rare on Mars to see those. And we've only sampled small bits of it, but usually the higher resolution we look, the more we can see these. But again, I don't know how extensive these deposits are in terms of the whole planetary budget. So that is a good consideration, and it is something that we need to think about even, before we go looking for organisms. What is the budget? How much is there available, and where is it distributed, and how did it get to these places? So that's definitely something to think about.
Just gonna have to wait till the first paleontologist gets on Mars.
Yeah, absolutely.
I volunteer.
Yeah, maybe.
You volunteer, yeah.
Yeah, if we go to Mars and dig a fossil, I hope we can find some life from like plants or animals in Mars. So what is it like?
Yeah, that would be quite a discovery.
This is a pretty exciting time in Mars research, with 3 spacecraft either there or just about to be there.
Absolutely.
Imagine that there's going to be a tremendous amount of data coming back.
Oh, yeah, it will be absolutely amazing. And all of them at the same time. And it's just going to be huge advancements in these fields. It's well, if everything goes well in the next year.
Knock on wood.
Yeah.
I can't remember, is there going to be anything similar to ground penetrating radar in the next craft?
Yeah, absolutely. There is ground penetrating radar on Perseverance. Yeah, I don't know what they're planning to do with that immediately, but that'll definitely be interesting to be able to hopefully image some of the internal layers of the delta. That would be really, really cool to be able to see how far they extend, how many layers, how often do they happen, and hopefully shed some light into intermittency and timescale as well.
I thought I heard about some upcoming mission that was going to Phobos, that they were looking to see what pieces of the Mars atmosphere had basically been interacting with Phobos. And in that respect, I suppose maybe you could look at an isotope ratio for oxygen and see if it came from atmospheric oxygen or from rainfall.
Absolutely. Yeah, I actually heard something about this as well. That would be, yeah, it's really cool that we're really sort of splitting forces into Mars. And, we've got a rover now, we've got the weather one, we've got a bunch of different things that really are going to come at it from different angles. And I think
Curiosity is still working, and I think Opportunity is still getting back some data. I'm not Spirit's done.
Yeah.
But Curiosity is still going to be working to send back data. A lot of data from Mars.
Absolutely. And it's also really interesting because, Curiosity is it's also in the lake system, but it's in a slightly younger lake system as well. So it's more in the Hesperian towards the Amazonian period, which is not quite the period where you have these valley networks forming. So Curiosity has been really important for understanding the importance of water later on in the Mars system, whereas we're going to go much deeper into time in Jezero crater. So that's why it's even more interesting for geomorphology and understanding water on Mars, because this is really where water was having its prime time on Mars. It's going to be cool.
Is the mineralogy on Mars similar to that of Earth?
As a person who is not a mineralogist, I know that most of the analog work and most of the geochemists usually like to work in Iceland. So I think Iceland would probably be one of the closest systems in terms of mineralogy and geochemistry that there is to Mars. And so, yeah, a lot of the analog work is done there. Some of it is done in different deserts and different landscapes, but I think a recent study just came out last month, which basically looked at all the geochemistry of different volcanic terrains and said that, well, actually, Iceland is probably the closest one we have so far from the data we have from rovers so far.
Yeah, they even got initial data from Pathfinder, the first rover, on just basic chemicals compared with Mars and surface with Mars and Earth. That was done, my God, that was decades ago for Pathfinder.
Mm-hmm. Yeah, absolutely. And, each new place we go to with these rovers, each centimeter, each meter we take, we find new abundances and things that we didn't expect. So it's always changing. And I guess we'll see what we find in Jezero. Again, it's a place full of carbonates, so that'll be really interesting to look at that as well.
Okay, anyone else have questions?
I have
As a personal question, do you feel that there was any potential for life on Mars?
I think I would like it if it would be quite scary if we found there's no potential for life now. I think there was potential for life before. I don't know how it would feel personally if we found it, because it would mean that life is common in the solar system, which is a really scary thought. The fact that there is no life is just as scary as that there is life. So honestly, I'd rather not even think about.
I don't know if you guys remember, but there was a guy named Gary Larson with his Far Side cartoons.
Oh, sure.
And one of them was one of the Soviet landers landed, took a couple pictures, and then went dark. Well, on Gary Larson's cartoon, you see a Martian coming over and switching off the rover or the camera. So, hello, Gary Larson. I don't know. You guys may be too young to remember the Far Side cartoons, but anyway.
I have a less scientific question. How did you personally get so interested in Mars? What happened in your studies that sort of moved you in this direction? Because you're obviously really passionate about this.
Yeah, that's a great question. I guess it starts further back than my actual studies. I think my dad was always very passionate about both the natural environment. He was a biologist, but he was always had a soft spot for space. So he would take me out to look at the stars, and he taught me all the constellations, and he bought me a telescope and always got me into that very early on. And so I think when you ask kids when they're 3 years old what they want to be, my first answer, I think, well, actually I didn't know, and I think I asked my aunt, well, what do you mean what I wanted to be? And she's like, I don't know, do you want to be like an astronaut? And I was like, oh yeah, I want to be an astronaut, but I never really knew what it was. But I guess it just kind of stuck. I've always enjoyed looking at space and thinking about space. And I think my degree was actually in earth sciences, but my master's thesis was on Mars, looking at landslides on Mars and what the shape of landslides tell us about whether there was ice or water when they were flowing on top of the substrate. But then my whole PhD was on Earth. And so I'm more trained as a terrestrial scientist. And it was only in my postdoc now, where I'm at UT, where I actually basically went full planetary, which is what I always wanted to do in the end. But I did want to have the training as a terrestrial scientist, because I think that's what sets you apart as a planetary science, to really actually understand Earth first before you go off looking at other systems.
Really?
Your thesis on the landslides in Mars, were they mainly concentrated in the Valles Marineris?
Exactly. Yeah. So only in Valles Marineris.
Okay, I've seen papers on those on the landslides. Really neat.
They're beautiful. They're gorgeous. They're like 200 kilometers of a huge deposit. It was actually really annoying though, because I finished my thesis and I was just writing it for the first time for publication, my first publication. And then as I started writing it, a group of planetary scientists from Italy published landslides in the Valles Marineris rift on Mars. And so that was my entire thesis just published in front of me. Of course, they had it was their own thing, but it was just a huge coincidence that we'd been working on the exact same thing, which was a shame, but it happens.
So what time is it in the UK now?
It is 3:27 a.m.
Sweet dreams.
If there aren't any more questions, this young lady needs to go to sleep.
Thank you so much for.
Thank you very much. It was very good.
Yes, thank you very much.
Being up for us.
No, it was great. It was a great opportunity to talk about all of this. So thank you for listening.
Thank you very much.
Thank you.
It was
Yes.
a
Thank you.
wonderful presentation. Thank you so
Thank you.
much.
Thank you.
So
very much.
anybody wants to stick
you.
around, please do. But thanks. It was a great talk.
Yes.
One little question. I'm editor of the newsletter for ESCONI. Could you write up a little summary and include a couple or 6 slides, and we'll put it out in our little newsletter?
Absolutely. Yeah, I can do that.
Okay, good. I'll remind you of that.
Okay.
Sometimes it takes 10 out of 10 reminders, but we'll try.
Not with me. Maybe only 9. All right. Thank you very much.
Thank you.
Thanks again.
Thank you.
Thank you.
Bye. Thank you.
Thank you.
I have a interesting little story. About 15 years ago, I took a 1-week geology course, college credit, with Gordon Baird.
Oh, Gordy.
Oh yeah.
And a hard rock geologist, Dr. Jack Berkeley, who his big thing was studying meteorites. So we went up into Canada from Buffalo area. We went up into Canada, and we covered the whole area, a huge chunk of Ontario. And there was a paleo side, which was with Gordon, of course. But on the other half of it was, again, hard rock geology. And we went to this one place called Theo's Flow, which was a volcanic igneous site that they correspond to 3 different situations. And what I mean by that is that these basalts that go back, I don't know how many, hundreds of millions, I mean, more like billions of years up into Canada, was also this meteorite that fell in Egypt called, I think if I remember correctly, it was the Nuclite meteorite, which they thought was a meteorite from Mars. So they kind of had this equivalent of the makeup of this Martian meteorite that fell in Egypt, like in 1911, to this site up in Canada called Theo's Flow. And they kind of think it was the same kind of makeup of the rock of this Martian meteorite. So there you go.
I'm discontinue recording, just so you know.
Yeah.